Assalamu alaikum. Hope you are doing fine. We have learned about electric cell. It is a device that converts chemical energy into electrical energy. When several cells are connected, it forms a battery. In this video, we are going to learn about series combination of electric cells. We will discuss what happens to the electric current and voltage when cells are connected in series. Here I have connected three cells in a series. When I say series combination, that means I connect the positive terminal of first cell to the negative terminal of second cell. The positive terminal of second cell is connected to the negative terminal of third cell. Here a positive terminal of third cell and the negative terminal of first cell are free. They act as the positive and the negative terminal of the battery. Battery means the combination of cell. Here these three cells are connected in series and it forms a battery. Now first I will check the EMF of these three cells individually. Then I'll find out the total EMF. Then we will also measure the current supplied by these three cells individually, and then we will measure the total current supplied by these three cells in a series combination. For that I am going to use this multimeter. First I will check the EMF. I have set this multimeter to read the EMF. Here the potential difference between the ends of a cell is referred as EMF when the cell is not connected to any device, or voltage in open circuit is referred as EMF. I'll place the black probe of multimeter to the negative terminal of the first cell. Then red probe is connected to the positive terminal of first cell. By doing so, it gives me EMF, which is nothing but 1.55 volt, as shown by the multimeter display. Now I will check the EMF of this second cell. It is again 1.55 volt. I will check the EMF of the third cell by following the same method. It is 1.56. So all these three cells have EMF around 1.5 volt. Now I will measure the total EMF of the series combination of these three cells, or I can call them as battery. To do so, I place the green wire on black probe, which acts as the negative terminal of the battery, and the yellow wire, which acts as the positive terminal of battery, to the red probe. You can see the multimeter reads 4.67 volt, which is the total EMF of this battery, which is formed by the series combination of these three AAA cells. From this, it is clear that The total EMF is the sum of EMFs of individual cell. You can see. Okay. Now I'll go ahead. Now we'll measure the current supplied by each cell. Then the total current supplied by the combination of these three cells. Now you always remember, a voltmeter is always connected parallel to a cell to measure the voltage or EMF, and ammeter is always connected in series to the cell or battery to measure the current. When I use this multimeter as a voltmeter, I connected the probes across the battery or cell. That means I have connected the multimeter in parallel. When I use this multimeter to read current, I have to connect this multimeter in series with the cell or battery. For that, I use one LED. Here I have three LEDs of different power rating. Out of them, the power rating of this LED is least, minimum. So I'm going to use this one to measure the current supplied by a single cell. We'll see. I will set this multimeter to read current up to 200 microampere. Here one thing I want to show you. Beside A, you may find a line, a straight line, that shows that it reads DC current. And beside V, if you find a straight line, that means the multimeter is set to read DC voltage. And here you have curved line beside V. It means it reads AC voltage. Now I'll connect the negative terminal of this LED to the negative terminal of the first cell. This way, then black probe here, then red probe is placed on the positive terminal. Now when I touch this, look at the LED carefully. What happened? It glows, but the glowing of LED is really hard to see. And here the multimeter reads 3.2 microampere. This much current is supplied by a single cell. Now I am going to place this probe at this end. When I do so, I am passing more current through this LED. See, now it glows bright. Now the multimeter is reading 1. That means I have to increase the range. See, again I have to increase the range. Again. Okay, now the current passing through this LED is 46 milliampere. It is 45 milliampere. Okay, anyhow, now if I connect these two terminals, it will destroy this LED. It can handle voltage up to 3 volt. So I'm going to remove this and replace this with this LED. Connect the negative terminal. Now I'll place it here. I'll set this to read up to 200 microampere DC current. I place black probe connected to the LED. I'll place this red probe on the positive terminal of this battery. See, it glows. And the multimeter reads 76 point something milliampere. I take it as 77 milliampere. That means 77 milliampere of current is passing through this LED. Now when I have connected the multimeter probe in this manner, that means the LED is connected in series with the battery. So this shows that when cells are connected in this manner, there is some variation in the voltage and as well the current. We'll discuss that in detail. To study the series combination of cells, I consider n number of electric cells connected in series. As you can see this diagram. Here I have connected the negative terminal of first cell to the positive terminal of second cell. Then the negative terminal of second cell is connected to the positive terminal of third cell and so on. Here this is the first cell and this is the nth cell in this diagram. All these electric cells have same EMF denoted by letter psi. It is read as psi, a Greek letter. It represents EMF of a cell. And apart from this, these cells have some internal resistance represented by letter R. Here I have taken R as the internal resistance of individual cell. It shows that all of them have the same internal resistance. Now, this series combination is connected to an external resistor of resistance capital R. If it is so, the total EMF can be obtained by adding the EMF of individual cell. Total EMF of a battery, I can call this. It can be obtained by multiplying the EMF of a single cell with the total number of cells. Here we have n number of cells. It gives me total EMF. I take it as equation number 1. Then the total internal resistance offered by all these cells is obtained by following the same method. Now, the internal resistance of single cell is small r. It is obtained by multiplying with the total number of cells. This gives me total internal resistance. Now I will find out the total resistance of this circuit that can be obtained by adding this external resistance to the total internal resistance as they are in series. Now, total resistance of this circuit is obtained by adding total internal resistance with the resistance of external resistor. This is taken as equation number 2. Now, I am going to use Ohm's law to find the current in this circuit. I consider I as the current flowing through resistor R connected in series to this battery. See, what is Ohm's law? We know Ohm's law is nothing but V equals to I R. Now from this, I value can be obtained by taking R that side. So R will divide. This is a I. Now current in the circuit is obtained by dividing total EMF with the total resistance. Total resistance. So I take the current in the circuit as I. Total EMF is known to us. It is nothing but N psi upon N R plus capital R. This is the equation. I take it as equation number 3, and it gives me the current flowing in the circuit. I box this equation for better visibility. I highlight this. Now we will discuss two special cases. I take case 1, in which I consider R, the internal resistance offered by individual cells, to be very small compared to external resistance. When R is taken very small, that means NR in equation 3 is neglected. Because when we multiply n with small value r, it is going to be a very small value. Adding that small value with a large value doesn't make any big difference. So it is neglected. So equation 3 appears something like this. N xi upon capital R. This can be written as N xi upon R. Here xi upon R is taken as I1. So N I is equal to Ni1. Here I1 is the current due to a single cell. This shows that current due to the battery will be n times the current due to individual cell. when R is very small compared to external resistance. Now I will take another case. The case 2, I consider a cell or cells with internal resistance greater than the external resistance. Here I take R, small r, to be greater than capital R. In this case, when R is very large compared to capital R, we need to neglect capital R for equation number 3. So R is very small, so it is neglected. R is neglected. There R is negligible, so we neglect it for equation number 3. So equation number 3 is written in this way: I is equal to N psi upon N small r. Here the same terms get cancelled and we obtain xi upon small r. This is xi upon small r is nothing but the current due to an individual cell. And this equation says that the current due to a battery is equal to the current offered by an individual cell. So currenting cells having large internal resistance is of no use. They do not find any kind of advantage. I hope this video is useful. If you have any kind of doubt related to the topic, kindly put a question in the comment section. Thanks for watching.